Hi, welcome to this new lesson. We've seen in the previous lesson how to train the neuron with just one image. We had the vertical line in the previous image. And now we're going to see first how to add multiple images to the neuron for the training, and also second, how to train the neuron with multiple images. We're going right away right now into the code to understand exactly each step that we need to take to add multiple images. Let's start. This is our neuron right now. We have first the input where we have the image preprocessing. In this case, we are loading only one image, the vertical line. We are preprocessing the image, so we're dividing each pixel by 255 so that the values of pixel goes from 0 to 1 only and not from 0 to 255. We're going to flatten the image, so we don't have the image as we see it like a square, but we have the square flattened in just one single line. So instead of 3 by 3 pixels, we have just one line of 9 pixels. And so to multiply this image in just one line, we added then the weights, and also the weights, exactly like the flattened image, is an array containing 9 numbers in just one line. Then we created a loop so that we could decide how long, how many epochs to train our neuron, and we tried with different number of trainings. We tried like with few trainings, 1, 2, and then 100 to have a better result. Then here inside is the core of our neuron. We multiplied the weights with the image flattened and we make the sum. Then to decide if our image is a vertical line, so if it's closer to 0, or a horizontal line, so closer to 1, we put this value when we multiply the image with the weights inside an activation function, which was the sigmoid, which gave us a result from 0 to 1. And already we were able to detect the output. The neuron was already able to tell it is a vertical or a horizontal image. Then to train the neuron, we added the error. So we were checking how far we were from a correct prediction by removing the label. So the vertical image had a label 0 from the result. Considering the error, then we were able to make an adjustment. So multiplying the error with the slope of our activation function for the result, we were able to understand how much to make the adjustments, and then on each loop we were making the adjustment on the weights. This was just a quick recap of how our neuron works. Now let's go right away and add another image. So to add the other image, we need to work at the beginning where we give the input. Here we have EMG, so we have the vertical image. Now let's add the second image. We have EMG2 and is equals to cv2.im read. We have the image on images. The image is horizontal.png, and then cv2.im read grayscale. As we did for the first image, also for this one we need to do some pre-processing. So EMG2 is equals to EMG2 divided by 255, and then we need to flatten the image. EMG2 flatten is equals to EMG2.flatten. And now this is the first image and this is the second image. Is this enough to add an image? Of course not. If I run the code, of course the code runs correctly, but we're not taking the second image. the code is running correctly, but it is only taking img flatten, so it is the first image, and here we are doing each operation with the first image. Instead, if we want to work with multiple images, we need to have all these values in just one array, not just the images separated. So that's why we will create a new array, and I will call this dataset. And in this dataset, we're going to put both images. So our array will look like this. Dataset is equals to mp.array, and inside we're going to put img flattened and then img2 flattened. So if I print the dataset, and let's print dataset, and I run this one, I go at the beginning where I have the dataset. So dataset is containing first image, which is the vertical line, so 0, 1, 0, 0, 1, 0, 0, 1, 0, and then the second image, the horizontal line, 0, 0, 0, 1, 1, 1, 0, 0, 0. Is this enough? It is not enough, because now we need to make all the changes inside the neuron so that it takes not only the first image but all the images that are in the dataset. Now we have 2, but we could have thousands of images. So let's make all the changes inside the neuron to take all the images. And so let's check what we can change. Of course, the weights will stay the same. Let's put just one round, just to make at the moment things simpler once we run the code, and then we can put as many rounds as we want. Then we are on round 1. So what happens on round 1? On round 1, we find the result for just one image. Instead, we want to find this result for all the images in the dataset. So one simple way that we could do to take all the images will be simply to loop through this dataset. So we could make, for example, for image in dataset, and we need to change the indentation of this one to put everything inside this loop. So we're going to put everything inside this loop this way. So once we loop through the image, of course, we want to take the image from the dataset, not any more image flatten as before. But first take image flatten and then image to flatten and all the images that are in the dataset. Then let's simplify this as much as possible. So we don't need right now to take any more the output inside when we're looping through the images. So let's instead put this at the end of the code. And I'm also going to comment everything for the moment. Okay, this one should be exactly at the end of every loop. So exactly this way. Instead, we loop through the image. Let's now run this. So we have the dataset. We have 2 images inside, then we go to train the neuron right away. So on the first, as first thing here, we are printing which round we are in, and then also let's print which image we are analyzing. So from convolution we can say print image, and then we print image, And let's run this and let's see what we get. So we have round 1, we have the first image, so 0, 1, 0, 0, 1, 0, 0, 1, 0, which is the vertical image. For the vertical image, we find the error, how far we are from a correct prediction, and then the adjustment we need to make, and then we change the weights. Then we have the second image, 0, 0, 0, 1, 1, 1, 0, 0, 0, which is the horizontal line. And again, we get the error and we make the adjustment. Now, is this enough? Just putting the images this way to train the neuron? Well, if you followed carefully the previous lessons, you should be able right away to spot some error that I made on purpose just to make you understand better this process. And I'm going through all of it to make it simple to understand. So we have the dataset, we have 2 images, we have the weights, and then we loop. So we start with the first round of the training, and on the first round we want to find the adjustment values for all the images, not for only one image. So we make the convolution with where we multiply image with the weights, then we find the result and the error. Now let's focus on these exact lines. Error. We see error is equals to result minus 0. If you remember, the 0 is the vertical line, but here we're looping for all the images, and we have not just the vertical line, but we have also the horizontal line. So in this case, if we print like the error, it's correct for the vertical line, which is supposed to be 0, but it's not correct for the horizontal line, which is supposed to be 1. So we need to find a way to associate each image with its correct label. So dataset, the best way to do this is to add another array with the labels. So labels np.array, and here we have EMG flooding. EMG flooding is the first image, and we see the EMG flooding is the vertical. So EMG flooding is vertical, so 0, and here we say 0. And then we have EMG2 flooding, which is the horizontal image. We see horizontal, and horizontal is supposed to be 1. So if we had other images, each image which is vertical, we need to associate with 0. Each image which is horizontal, we need to associate it with 1. And this association is simple because we put everything in the exact order. So the first one on the dataset corresponds with the first one on the labels. So EMG flooding, the vertical is 0, this one. EMG2 flooding is horizontal, and it is this one. And so when we loop through each single image, so for image in dataset, we also loop through the labels. So we can do it this way: zip dataset and labels. So this function zip is used in Python to extract multiple arrays together. So we loop through dataset and labels, and so we have image and label also. And here we have label. So let's print the label. Print label and then label. And we can run this one. Now we see label 0 and label 1. This label 0 is telling us that the first image of our dataset is a vertical line. So 0, 1, 0, 0, 1, 0, 0, 1, 0. This label 1 the second image of the dataset is telling us that the second image is a horizontal line, 0, 0, 0, 1, 1, 1, 0, 0, 0. So why it is important to have exactly the label associated? It is important because we're going to make the adjustment based on the label. So when we calculate the error, we calculate the error on the first image by subtracting the result with the label. So the result with 0. So it will be in this case 0.81 minus 0. But in the second case, on the second image, we're going to subtract from the result, we're going to subtract 1. So that's why it is important to put the exact label on each image to tell to the neuron what image we are training exactly. Now, let's make a small adjustment on our neuron, because now we are adjusting the weights. In this case, for example, after the first image, we change the weights. So after the first image, the weights are 0.5, 0.32, 0.5, 0.5, 0.32, 0.5, 0.5, 0.32, and 0.5. And when we go to the second image, we're not using the original weights, but we are going to use the weights that are already adjusted from the first image, and that's not correct. On each round, we have to multiply the same weights for all the images. So on the first round, both the vertical image and the horizontal image need to be multiplied with the original weights, which are 0.5 for each number. So we don't have to allow to make the changes on each single image. Because if, for example, we had 1000 images, already on the first round, the image placed on the 1000 position will have the weights completely messed up from all the other images. And we don't want that. The images on each round must be multiplied with the same weights, and only on the new round the weights will be updated. So to make this adjustment, we need to take out the weights from the loop through the dataset. So simply we change the indentation and we put the weights just here outside. But we need to be able to keep track of the weights during the changes on the dataset. So to make this, we can create a temporary weights copy so that we can have them on the dataset. So we can say something like this: temporary weights is equals to weights dot copy, and we multiply. So we multiply each image for the weights, the original weights. But then when we make the adjustment here, we just make the adjustment with these weights minus or equals and p dot, it is not img flatten but the image. And also we're going to change the temporary weights, and then also weights, it is minus or equals weights, it is equals to temporary weights dot copy. I will run this and later I will explain exactly what it happened right now, especially why I did this operation. So let's quickly review the neuron. So we have our input, image preprocessing, we have a dataset with both images already preprocessed. To each image, we associated a label, so vertical image with 0, horizontal image with 1. The weights, we have 9 numbers, as many as the pixels are. Then we start with the round 1. On round 1, we want to multiply the weights for all the images in the datasets. To do that, we loop through the dataset with corresponding labels. We multiply now first image with the weights. So now the weights are 0.5, 0.5, all 0.5, and we multiply all 0.5 with the first image. When we are here at the end, our weights are changed. So we have temporary weights, we print temporary weights, and then print temporary weights. So we can see them. Temporary weights, after the first image, the temporary weights are changed. And they are not 0.5 all of them, but they are 0.5, 0.32, and so on, as you can read here. But then we have to multiply again the weights for the second image when we loop through a second image. And the weights, we don't want to use on the second image the weight adjusted, but we want to use the original weights of the first round. So that's why we're not going to change the weights right away, but we keep track of temporary weights during the loop of the dataset. And only after we loop through all the images, then we can change the weights, the original weights, with our temporary weights. And so what you see right here are our final weights after the first round. And now let's train the neuron a bit further, so I can cancel this temporary weights printing. It was just to give an explanation. And let's run the code, but let's put again 100 on the ranges. And after 100 rounds, these are the final weights. 0.5 minus 1.78, 0.5 1.97, minus 0.30, 1.97, 0.5 minus 1.78, and 0.5. And this is the neuron, so these weights are trained for both the label 0, so the vertical image, and the label 1, the horizontal image. And after 100 rounds, so here we see round 100, we can take a look at the errors. So here we have the error for the vertical image, which is 0.02, and the error for the horizontal image, which is minus 0.02. So with such a small error, we can say that the neuron has been trained correctly to detect the horizontal image and also the vertical image. We will see in the next lesson how to add different types of images and how to make the neuron a little bit more clever. This is all for this lesson. See you in the next lesson.